This is Sravanthi, working as Assistant Professor, Department of Chemistry in Institute of Aeronautical Engineering. Today we are going to discuss about thermo-response materials or thermo-response polymers. In this we will discuss about polyacryl amides and polyvinyl amides. So in previous class already we discussed about smart materials. So now let's discuss thermo-responsive materials. So it is also one type of smart material. So here this thermo-responsive material, it is also called as temperature responsive polymers. So here these are the polymers, that means thermo-responsive materials. These are the polymers that exhibits drastic and discontinuous changes. Drastic and discontinuous changes in their physical properties with temperature. Here thermo-responsive material, that means thermo means temperature. So these materials changing their properties with respect to their temperature. So that materials are called thermo-responsive materials or temperature-responsive materials. So it is one type of smart material. So smart material means these materials are having properties, so that properties change with external stimuli, that means pH, pressure, or any physical factors or environmental factors or any other chemical factors affecting on that. So it changes their properties with their external stimuli. That is called smart materials. So here thermal responsive materials, it is also a type of smart material. So they are these materials changing their properties with respect to their temperature. So here thermo-responsive materials are the polymers that exhibit drastic and discontinuous changes in their physical properties with temperature. Mainly these materials change their properties with temperature is called thermo-responsive materials or temperature-responsive polymers or temperature-responsive materials. So here these polymers are a class of smart materials. Just now we discussed already. So these materials are a type of smart materials, so that have ability to respond a change in temperature. So these thermo-responsive materials or thermo-responsible polymers are the type of smart materials or class of smart materials. So that means that the materials are having the ability to respond changes in temperature. Change in temperature. So these materials change their properties with temperature. So property that makes them useful materials in wide range of applications. Because of this property, that means these thermo-responsive polymers or materials change their properties with respect to temperature. So because of this property makes them useful materials in wide range of applications. So consequently it attracts much scientific interest. So research purpose, because of this property, most preferable and synthesize so many these thermo-responsive materials we can synthesize because of this property. That means these polymers change their properties with the temperature. So now recent years you observe that this review focuses mainly on the studies published over the last 10 years on the synthesis and use of thermo-responsive polymers. Synthesis and use of thermo-responsible polymers for biomedical applications. So biomedical applications such as, for example, drug delivery, tissue engineering, and gene delivery. So in this case, we have preferred this thermo-responsive materials. So thermo-responsive material means these are the polymers which exhibit drastic or discontinuous changes with their with temperature. They are changing their properties with temperature is called thermo-responsive materials or thermo-responsible polymers. So because of this property, we preferred these polymers in research field. So here the review focus mainly in the recent studies we observed that most preferred synthesis of thermo-responsible materials for used in biomedical applications. For biomedical applications, most preferable materials, these are the thermo-responsible materials. So biomedical application means here, for example, such as drug delivery, gene delivery, or tissue engineering. So, etc. Biomedical application purpose, we synthesize these thermo-responsive materials. In recent years, we observed that last 10 years, mostly research focused on this thermo-responsive materials synthesis and application used for biomedical application point of view. Most preferable materials are thermo-responsive materials. So here, thermo-responsive polymers are a class of smart materials. So smart materials means these are having property. So this property change with the external stimuli such as pH, pressure, temperature, or any other chemical compounds. So the material changes their properties. So the thermo-responsive polymers are a class of smart materials that have the ability to respond a change in temperature. So here thermo, that means temperature. So these polymers change their properties with their temperature. So that property makes them useful materials in wide range of applications and consequently attracts much scientific interest. So just now we discussed already. So these materials mainly synthesized for what purpose? Used in biomedical application point of view because of this property. They change their property with their temperature. So that's why most prefer this thermo-responsive polymers or materials and used for biomedical applications. So one of the main group of smart materials is based on polymers because these are cheaper and more easily tailored than metals or ceramics. So these thermo-responsive polymers are the group of smart materials that are based on polymers. So because they are cheaper, easily available and more easily tailored, that means we cut compared to metals and ceramics, easily we cut the shape. So that's why we prefer mostly this thermo-responsive polymers compared to metals and ceramics. So these polymeric smart materials can respond to stimuli. So generally smart materials means they change their properties with the external stimuli. So here these polymeric smart materials respond to stimuli, that means conditions such as the pH, temperature and ionic strength, electric and magnetic field, ligand or chemical and biological stimuli. So these thermo-responsive materials are the group of smart materials. They respond to external conditions, that means stimuli, that means such as pH, pressure, physical or chemical factors or any other chemical compounds. So they change their properties. So there are two main types of thermo-responsive polymers are there. So the thermo-responsive polymers means those polymers change their properties with their temperature. So if the temperature increases or decreases, properties can changes. So these thermo-responsive polymers are classified into two types: lower critical solution temperature, upper critical solution temperature. So lower critical solution temperature and upper critical solution temperature. So what is the meaning of this lower critical solution temperature and upper critical solution temperature? So these thermo-responsive polymers are classified into two types. So first we discussed about lower critical solution temperature. So the lower critical solution temperature or lower consolute temperature. Consolute means here two or more solutions. That means it is looking like a miscible, homogeneous solution. So the lower critical solution temperature or lower consolute temperature is the critical temperature below which the components of a mixture are miscible. This is the most important point. So here lower critical solution temperature or lower consolute temperature. So here is the critical temperature below which the component of a mixture are miscible in all proportions. It looking like a homogeneous system. Only one phase is available in lower critical solution temperature. For example, here this is in this graph, when we draw the graph between concentration and temperature. So here lower critical solution temperature. Here is the critical temperature below. So this below lower critical solution temperature, the components of mixture are miscible in all proportions. So here it's available only one phase, lower critical solution temperature, it is miscible. That is called LCST. So all are miscible in one proportion. In all proportions, it is a mixture or miscible, like homogeneous system formed in this lower critical solution temperature. So now what is the meaning of upper critical solution temperature? Upper critical solution temperature. So here upper critical solution temperature or upper consolute temperature. So consolute means just now discussed two or more components systems, binary compounds, etc. So upper consolute temperature is a critical temperature above which the components of a mixture are miscible. Above this lower upper critical solution temperature or critical temperature are above which the components of a mixture are miscible in all proportions. See here in this upper critical solution temperature. So above the upper critical solution temperature, it is a miscible. That mixture are miscible in all proportions. That means homogeneous, homophase. Homogeneous system is formed. It is miscible clearly. But below the upper critical solution temperature, we cannot miscible clearly. It is cloudy appearance here. It is a cloudy appearance because of this oil in water, like for example, emulsions. So two or three different phases available in that. But only upper critical solution temperature, in that case, the mixture components of a mixture are miscible in all proportions. So what is the difference between lower critical solution temperature and upper critical solution temperature? So here lower critical solution temperature. So it is a critical temperature below. In this lower critical solution temperature, so it is the critical temperature below which the components of a mixture are miscible in all proportions. You can miscible only the critical temperature, lower critical temperature. So one phase it is available. Above it is, we cannot miscible. You cannot miscible. That means it is different binary systems are available. Not heterogeneous system. That means it is cloudy appearance. So here upper critical solution temperature means it is a critical temperature above with the components of a mixture are miscible in all proportions. Here lower critical, below this, and upper critical above the. So in this case we can miscible all the components of the mixture are miscible at all proportions. So here lower critical solution temperature and upper critical solution temperature. These are the respective critical temperature points. These two are the respective critical temperature points below and above which the polymer and solvent are completely miscible. Completely miscible. For example, see here, when you draw the graph between composition, x-axis you are taking composition of variable, y-axis temperature. So here, see this lower critical temperature. Lower critical solution temperature. So it is a critical temperature points. Below this critical temperature, the polymer and solvent. Here, polymer plus solvent. Both are mixed, that means miscible. That means a homogeneous system formed below the lower critical solution temperature. We can miscible all the components in single phase, one phase only. But in upper critical solution temperature, so above this, it is a clear homogeneous solution. It is a clear homogeneous solution. That means polymer and solvent both are mixed, miscible. So clear homogeneous solution, while the polymer solution above the LCST. Simply we say in a lower critical solution temperature and upper critical solution temperatures are the respective critical temperature points below. In this LCST it is below, and UCST upper critical solution temperature it is above. So which the polymer and solvent are completely miscible. That means only single phase homogeneous system is available. But above the lower critical solution temperature and below the upper critical solution temperature, we cannot miscible clearly because here is present two phases. So thus, for example, a polymer solution below the lower critical solution temperature is clear homogeneous solution, while a polymer solution above the lower critical solution temperature appears cloudy. So it leading to LCST also being referred to as a cloud point. That means simply we says below the lower critical solution temperature and above the upper critical solution temperature, the components, mixture of components are miscible clearly. So it is a single phase system or homogeneous system. But above the lower critical solution temperature and below the upper critical solution temperature, the compound we cannot visible clearly. It is not miscible. That means it is a cloudy appearance. Two or more binary systems are available. So it is a cloudy appearance in that. So that is the main difference between LCST and UCST. So best example of this thermoresponsive materials or thermoresponsive polymers are the polyacrylamide amides. So what is the meaning of thermoresponsive materials or thermoresponsive polymers? So these materials are change their properties with respect to their temperature. Change their properties. Because of this reason, so these materials or these polymers most preferred in recent years in research. They synthesize these materials and use it for biomedical application purpose. So in this most important is polyacrylamide is one of the best example of thermoresponsive polymer. So among a variety of thermosensitive smart materials or thermoresponsive smart materials, here poly-N-isopropyl acrylamide, PNIPAM, poly-N-isopropyl acrylamide. So first reported in 1968. First reported in 1968. It is one of the most widely investigated polymer. So polyacrylamide is the best example of thermoresponsive polymer. So in this, among a variety of thermosensitive smart materials, most important is poly-N-isopropyl acrylamide. So first reported in 1968. So it is one of the most widely investigated polymer. So this PNIPM shortcutly has both hydrophilic and it containing both hydrophilic amido group and hydrophobic isopropyl groups. So this polyacrylamides, it has both hydrophilic and hydrophilic means water loving. That means simply it is easily soluble in water. Water reactions that takes place in this hydrophilic. What is the meaning of hydrophobic? That means it resistance to water. It not dissolved in water. It dissolved in, for example, oils, fats, for example. But here hydrophilic means it is dissolved in water like salts, ions. So here this PNIPM, that means poly-N-isopropyl acrylamide, or simply this is polyacrylamide. It has both hydrophilic amido groups and hydrophobic isopropyl groups. So when the temperature is low, there is a strong hydrogen bond between amide group and external water molecules. So these polyacrylamides are having both hydrophilic amido groups and hydrophobic isopropyl groups. So here when the temperature is low, because it is a thermoresponsive polymer, it changes its properties with respect to temperature, right? So here when the temperature is low, so there is a strong hydrogen bond between amide groups and water molecules and external water molecules. So this PNIPM is polyacrylamides is hydrophilic. Macroscopically, swelling occurs for the volume. Swelling occurs for the volume, and when it interacts with water and dissolved in water, so here swelling occurs for the volume. So here, so when the temperature reaches the lower critical dissolution, when the temperature reaches lower critical dissolution temperature, that means LCST, lower critical solution temperature, it reaches, the hydrogen bond between amide group and water molecules is destroyed. That means the hydrophilic nature converted to hydrophobic. So when the temperature reaches the lower critical dissolution temperature, so the hydrogen bond between amide group and the water molecules is destroyed. So the hydrophobicity of the isopropyl group in the structure plays as a leading role. Now that means hydrophilic converted to hydrophobic. So in this, that means here hydrophobicity of isopropyl group in the structure. So that plays a leading role, important role. So and this polyacrylamide or PNI-PAM becomes hydrophobic and gradually shrinks. Now it is becomes hydrophobic. So this polyacrylamides are having hydrophilic and hydrophobic isopropyl groups. So now many studies have shown that the lower critical solution temperature of polyacrylamides or PNI-PAM is about 32 degrees centigrade. So many research studies shows that what is the lower critical solution temperature of polyacrylamide or PNI-PAM is about 32 degrees centigrade. So which is close to physiological temperature and easy to adjust. So it has been developed for biomedical. So many research studies it tells that that lower critical solution temperature of PNI-PAM or polyacrylamides is about 32 degrees centigrade. So which is very close to physiological temperature. So that is it is easy to adjust. So it has been developed for biomedical applications. So such as for example drug delivery systems and cardiovascular repair and sensing analysis, medical imaging and so on. So many biomedical application purpose these thermoresponsive polymers most preferred and preferably synthesized for biomedical applications. So this is a structure of polyacrylamide or PNI-PAM. It's a structure of PNI-PAM, polyacrylamides groups here, and it is having hydrophilic and hydrophobic groups, right? This PNI-PAM polyacrylamide, it is having a hydrophilic and hydrophobic. So it is at lower temperature. So it is having hydrophilic nature, the strong hydrogen bond between amide group and external water molecule. But lowest critical temperature, this the amide group and water molecules is destroyed. That means it becomes a hydrophobic nature. Hydrophobic nature. See here, 32 degrees is the lowest critical solution temperature of polyacrylamides or PNI-PAM. So above this temperature, so below this temperature it is having hydrophilic nature. Hydrophilic nature. Above the temperature it is having hydrophobic nature. So what is the thermoresponsive property of this polyacrylamide? Polyacrylamide. So what is the thermoresponsive property of polyacrylamide? So first, what is the meaning of thermoresponsive polymers? So these polymers change their properties with respect to their temperature or external stimuli. So here poly N isopropyl acrylamide is all a well-known thermoresponsive polyacrylamide. So it is one of the example or one of the type of polyacrylamide. So it has a lower critical solution temperature is around 32 degrees centigrade. Just discussed already. So lower critical solution temperature range of polyacrylamide or poly N isopropyl acrylamide is around 32 degrees centigrade. So below this temperature, this PNI-PAM shortcut, it is water soluble. Below this temperature, it is water soluble. That means the nature is hydrophilic nature. Hydrophilic nature. But above the lower critical solution temperature, it becomes hydrophobic. It becomes hydrophobic. That means the hydrogen bond between amide groups and water molecules is completely destroyed. So above the lower critical solution temperature, that means above the 32 degrees centigrade temperature, so it becomes hydrophobic and undergoes a phase transition. phase transition, and precipitating out of solution. Precipitating out of solution. So this is the thermoresponsive property of polyacryl amide. So what are the applications of this polyacryl amide or poly-N-isopropyl acryl amide? So this and other polyacrylamides and poly-N-isopropyl acryl amides with similar thermoresponsive properties have applications in drug delivery, tissue engineering, and as components in smart materials. But most important is these materials used for biomedical application point of view because of that property. Their properties with respect to the temperature, their properties changes. So because of that, these materials mostly preferred in this biomedical applications. So one more example is polyvinyl amides. So among the thermoresponsive polyvinyl amides or poly-N-vinyl caprolactam. Among us thermoresponsive polyvinyl amides, poly-N-vinyl caprolactam, VNVCL, polyvinyl caprolactam. So it is a well-studied temperature responsive polymer nowadays. And second only to poly-N-isopropyl acrylamide. So first one is, and all the thermoresponsive polymers, most preferred one is poly-N-vinyl caprolactam is a well-studied temperature responsive polymer. And second only to poly-N-isopropyl acrylamide, the most popular temperature responsive polymer. These two are the best example of thermoresponsive polymers. So what is that? Poly-N-vinyl caprolactam. This is the most preferred polymer. And one more example is poly-N-isopropyl acrylamide. It is also one of the example of most preferable thermoresponsive polymer. So these polyvinyl amides. So these polymers show similar lower critical solution temperature behavior in water at between 32 degrees centigrade. So lower critical solution temperature of this polyvinyl amides and polyacryl amides are 30 to 32 degrees centigrade. So this is the preparation of polyvinyl amides, that means poly-N-vinyl caprolactam synthesis preparation, and the synthesis of poly-N-vinyl caprolactam COOH polymers by free radical polymerization of using a modified version of the protocol. So what is the thermoresponsive property of polyvinyl amides or poly-N-vinyl caprolactam? So this poly-N-vinyl caprolactam is an example of polyvinyl amide with thermoresponsive behavior. So it exhibits a similar lower critical solution temperature as polyacryl amide. So making it soluble in water below the lower critical solution temperature and insoluble above it. So what is the temperature range of this polymers? 32 degree centigrade or 30 to 32 degree centigrade temperature. So lower critical solution temperature of poly-N-vinyl caprolactam and PNIPAM, polyacryl amides. So this lower critical solution temperature, it is similar, that is 32 degree centigrade. So in this temperature range below this 32 degree centigrade, it is a homogeneous system, that means single phase, the components mixture is visible. But above this LCST, it is insoluble above it. That means binary systems, cloudy appearance, it cannot visible clearly. So what are the application of this polyvinyl amides? So these polyvinyl amides are used in various applications including drug delivery, flocculants, and the formulation of responsive coatings. So simply we say thermoresponsive polymers mostly preferred in biomedical application purpose because of their property. So thermoresponsive polymers are change their properties with the temperature. So because of the property, in last 10 years, we observed that in research studies, most prefer this synthesis of thermoresponsive polymers for biomedical applications like drug delivery, gene deliveries, and flocculants, etc. We are using this. So today's session, we'll learn about what is thermoresponsive polymer or temperature responsive polymer. Best example of polyacrylamide and polyvinyl amides. What is the lower critical solution temperature and higher critical solution temperature ranges? We'll learn in this session. So I hope understood all. And last one is, so in both the cases, in both the cases means lower critical solution temperature and higher critical solution temperature. So the responsive behavior of these polymers allows for controlled changes in their solubility. So what is the conclusion of this thermoresponsive polymers? So in both the cases, the thermoresponsive behavior of these polymers allows for controlled changes in their solubility. So which is advantageous for application where temperature dependent properties are desired. So these properties can be harnessed in drug delivery systems where the polymer can act as carrier that releases in payload response temperature changes. So in the smart material application point of view. So additionally, the lower critical solution temperature of these polymers is often close to body temperature. So making them particularly suitable for biomedical applications. So simply we say that thermoresponsive polymer, they change their properties with respect their temperature. So because of that property, we preferred in biomedical applications. We synthesize this material for biomedical applications. And it is a lower critical solution temperature is 32 degrees centigrade. It is related to atmosphere temperature. So easily we can adjust it. That's why we most preferred in this biomedical application, most suitable this one, drug delivery systems for example. So I hope understood all. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.